Okay, this is the second screencast in which I describe the constant rank theorem. It depends on the inverse function theorem, which I covered in the first screencast. This theorem is the main local classification result for smooth maps between smooth manifolds. Okay, so the theorem basically says that if if we have a smooth map between two manifolds of any dimension, and if this map has a derivative with constant rank in a neighborhood of a point, and it's important that this is holding in a neighborhood and not just at the point, then this map is equivalent to a linear map which takes the m coordinates and just projects to the first k of them and then puts everything else to zero. So this is a linear map. So notice that, let me just write this. So this map is a linear map which consists of a projection map. So I'll put a double arrowhead to indicate that this is surjective. It's a surjective linear map to Rk followed by an injective map from Rk to Rn. So it's basically describing the linear map in a simple way as possible. Or another way of saying it is that the map looks like an n by m matrix where we have a k by k identity matrix in the top left and then zeros elsewhere. Okay. So the first step, well, okay, before the first step, we have the 0th step, which is just a setup of the problem. So this is gonna, since this is the local theorem, we can choose charts so that we could consider M to just be an open set in Rm and N to be, again, just Rn. So we have now a map between Euclidean spaces, and we can arrange that the charts are chosen so that the point P that we're interested in is just the origin, and it's sent to the origin. So we basically have a map from Euclidean space to Euclidean space, which sends the origin to the origin. This is a nonlinear map, and we're trying to show that there are coordinates charts which make the map this into this simple form. Okay, so what do we know? We know that the derivative of this map has rank k. Now the derivative is an n by m matrix. Okay, and if we know that it's of rank k, that means that there is some k by k minor somewhere in there whose derivative, which there's some k by k minor that is non-singular, meaning that its determinant is non-zero. So what we can do is reorder the coordinates. We can just permute the coordinates on the domain and on the codomain so that it's in the top left corner. So now the derivative has a non-zero, a non-singular k by k minor in the top left corner. And these coordinates, these reordered coordinates, I'm writing them in this way. So we have x's for the first k in the domain and y's for the rest, and u's for the first k in the codomain and v's for the rest. Okay, and just for convenience, you can refer to this k tuple as x and this m minus k tuple as y, and so on for u and v. So with this kind of shorthand notation, I can write my map. It has inputs x and y, and the output has two components. The first component I call q, and the second component I call r. So q actually has k components, and r actually has n minus k components. And I've written here that q is really the map composed with the projection to the first k variables. So just because there are many components, I'm just kind of combining these k components into one map q. and similarly for this into one map R. Okay, and we have arranged this so that the first k coordinates on both sides, if we look at this Q map, we've arranged it so that this k by k minor inside the derivative is going to be non-singular. So if I compute the derivative of this map, I get a block matrix where the first k by k block is the derivative of Q with respect to the x. And so this actually has, k squared components, which are all derivatives of the components of Q with respect to the first k variables. Anyway, the point is that this minor has been arranged to be the non-singular one, and that is the setup that I want to work with. So, so now the strategy is that we want to change coordinates on the domain, and we want to change coordinates on the range or on the codomain in such a way that if we now rewrite this map in these new coordinates on the two sides, then the map looks really simple. It looks like that linear map that we discussed, just projection to the first k variables. Okay, so the first step is that we're going to define this coordinate change, the phi. So this is the coordinate change on the domain. Okay, and the idea is that if we're just, so the first step is that we want to define a coordinate change on the domain, which puts the Q into normal form. So we're focusing on Q. So suppose we consider a map on the domain. So it's going from Rm to Rm, taking xy to Q and y. So it does nothing to the second variable, leaves it alone. The first variable is sent to Q of xy. So the reason why this is an important map to consider is because we know that, so if we compute its derivative, we'll get that we get this same minor showing up again. Okay, and then Q obviously could have a y dependence, but the rest of the derivative matrix is very simple. It's just a zero matrix, and then an identity matrix, since y is just sent to y. So if you want to determine the properties of this derivative, because it's an upper triangular block matrix, it's easy to determine when it's invertible, because the determinant of a block matrix is just the determinant of the the determinant of an upper triangular block matrix is just the determinant of this times the determinant of this, and this is just 1. And so basically, because of the fact that we know that the first k by k block is invertible, the whole thing is invertible. So that means that this map has an invertible derivative at 0. And that's why we can use the inverse function theorem to invert it. And whatever this inverse is, which is guaranteed by the inverse function theorem, I'm just going to write it in this way. It'll take xy to a and b, two functions of x and y, and all we know is that this is the inverse of this map, phi. So if we write that fact, the fact that this is the inverse of phi, then we see that xy must be sent to xy if we apply the phi inverse and phi. And if we write that out, this inverse takes xy to ab, and then phi takes ab to q of a, b, and b. So that means that xy must be equal to this function q composed with the functions a and b in the first component, and then b in the second component. So that implies that b has to be just y. So that allows us to kind of solve for what b is. Okay, so if we try to see what happens if we make that change of variable and then compose it with f, so this means that we're now re-expressing f in the new coordinate system on the domain. What is it going to do? It's going to take xy to x, okay, and some function which is, let's look again at this function f. So f, remember, is just made up of two components, q and r, right? So, right, so this means that x and y are going to be sent by phi inverse to a and b, but then we're applying f to this, and we know that the first component of f is q. So when we apply q to a and b, we're going to get just x back again. So this explains why x is just sent to x, okay? So in other words, we have successfully kind of eliminated or removed this complicated q component. We've kind of inverted it, and now the first component of the new map is very simple. There's no q here, it's just x sending to x. On the other hand, y is sent to the composite of r applied to the a, b components of the inverse. So this is just composing this, and we see that we have some function of x and y, which is the composite of r and a. Okay. If we compute now the derivative of this map, we see that it is now going to be actually a lower triangular block matrix, precisely because the first component does not have any y dependence. So we just get a k by k identity matrix, 0, and then the x and y derivatives of this s function. So I'm just computing the derivative here. And here we see right away that there's an important property of S, which is that this, all I've done here is to change coordinates on the domain and compute the derivative of f in this new coordinate system. We knew that f had rank k. The derivative had rank k originally, and now I'm just changing coordinates. So this derivative must also have rank k. But if we look at the block form of it, we have a k by k identity matrix here. So the only way that this matrix can have rank k is if this part is just completely 0. And what that means is that S does not actually depend on y. Okay, so because of the way that A and B, so the fact that A, B are the components of the inverse, that eventually implies that when I compose R with A, I get some function of x and y which actually doesn't depend on y. Okay, so that means that the form, after I've changed coordinates on the domain, the new function, it takes x and y to a point x and s of x, which means that I've completely eliminated the y dependence by doing this change of variables. So it's not quite doing what I want. It's not just projecting out the x components, because this is not 0 here, but this second component actually has no y dependence. So that's the result of doing the first change of variables. In the second step, I want to change coordinate on the codomain. So what I'm going to do is I just want to eliminate this this s function. So I'm going to define a diffeomorphism of Rn, which takes uv and sends it to uv, where I shift the second component by subtracting s of u. Okay, so this map, where I'm just doing like a shear transformation, is clearly a diffeomorphism because it has an inverse where I just subtract s of u rather than oops, sorry, this should be adding it. So so that means that if I simply just add s of u, then this transformation is the inverse of this transformation. Shear transformations of this type are always diffeomorphisms for the same reason. And because this is a diffeomorphism, then obviously I can use it as a coordinate change on the codomain. And if I compute my function now in the new variables, what does it do? It takes xy to x s of x, and then I just subtract this off by applying this psi, and I just get back to x 0. So that second change of coordinates is very easy to find because I've done most of the work already by removing the y dependence altogether from the map F. Okay, so that shows you the proof of the theorem and how it basically depends on just setting it up so that the first k components of the map have an invertible derivative. You use the inverse function theorem to invert that q, and then we just fix up the rest by doing this shear transformation.